Welcome back to Linear Algebra 101. This is a series where we're going to teach you basically everything there is to know about linear algebra in a way that's hopefully easier to understand, and it's going to take you through the basic steps as we go. Today's topic, we're going to basically introduce a theorem based on the stuff we learned in part 1. And our goal of it is to introduce you into a more broader mathematics, which is what linear algebra is all about, as well as your first introduction into mathematical proofs. For a lot of you, this is kind of your first, and you're required in classes to do both at the same time, which is why linear algebra becomes really hard as a course for a lot of people. So don't fret, just understand this is very difficult for a lot of people, and you're not alone in this. Hi, my name is Mac. I'm going to be your math tutor for today, and this is Linear Algebra 101. So let's recap everything that we learned last time in part 1. Basically, the first thing we learned was something called a Euclidean space, just denoted Rn. And this was a very fancy word that mathematicians use basically just to describe the real numbers in multi-dimensions. So R2 is essentially everything that represents 2D. R3 is everything that represents 3D. And once you get to 4, this is where it represents everything in 4 dimensions. Now again, we can't exactly visualize that, but this is the idea of it. And Rn is everything that can be represented in R dimensions of real numbers. Okay. The second thing we learned was something called vector addition. This is the idea of if you add a vector x and a vector y together, this is just the summation of each of the elements together. Very straightforward. And the final thing we learned was scalar multiplication. Basically, if you multiply a real number by a vector, this just becomes the c is now multiplied by every single element within x. So let's go over the goals of today. The first goal is we're going to introduce proofs and what they are. We're basically going to showcase how in math, how do we actually prove something mathematically through it? And what are the techniques and the things that we're looking for it step by step. And this is the type of techniques we're going to use later on, not only in this course, but in all of your future courses. The second is we're going to prove a very important theorem that comes from linear algebra right off the bat. And this is basically going to have 10 different statements to prove for each. And we're going to prove all of them as examples. Okay, so our first topic is going to be mathematical proofs and what do we do with them. The basic idea behind proofs is you are given a bunch of things in a statement, either a definition, a theorem, or a lemma. Lemma is just a mini theorem. And your goal is always to find the thing you need to prove. And this is almost always a definition. Almost always a definition. The goal of it is to basically use the definition you were given, and then using just some form of math or other definitions you were given to arrive at the definition of the thing you were trying to prove. This is unfortunately where memorization comes into play. So you have to remember, for instance, we're going to do an example in the second part where we're going to use the definition of vector addition. And we're going to need to prove something that is a definition of a vector in Rn. And so in order to do that, we have to remember specifically what the definition of vector addition is and the definition of something that exists within Rn is. And normally with math, we don't like things that are kind of memorization heavy. We like things that kind of just flow. So in order to truly engrave these definitions into our head, we're going to need to practice these. So let's move on to our next part where we're basically going to practice this same idea 10 times. Okay, now we're going to do our first example of proving a theorem. So this is an important one that will come on later when we start talking about vector spaces. So let x, y, and z be vectors within Rn, and c and d be real numbers. Then it shows that all of these 10 properties are true. X plus y is a vector within Rn. X plus y plus w is the same as x plus y plus w. This is the order of operations. X plus y is equal to y plus x. That means you can flip them and still get the same number. There exists a zero vector within Rn such that x plus 0 is x. And for every single x that is a vector within Rn, there exists an a, which we will call the inverse, such that x plus a is equal to 0. The scalar multiplication of c times x is a vector. C times d of x is the same as c times d times x. C plus d of x is equal to cx plus dx. C times x plus y is the same as cx plus cy. And 1 times x is equal to x. One of the reasons I specifically chose this example to be your first introduction into proofs is because a lot of these seem almost trivial, right? They're the same kind of properties that we have when we're just adding real numbers together that we would have before. Like saying 1 plus 2 is the same as 2 plus 1. That's a very obvious trivial thing. But that's why this is such a great example. Because they're trivial off the bat, you get to truly see how you do a proof in math. So let's get started. We're going to prove each and every one of these, starting with number 1. Okay, this is part 1. We're going to show that the addition of the vector x plus the vector y is an element of Rn. So let's recall our definition. In order for x to be within Rn, it is if and only if it is of the form x1 to xn, where each of the elements within it is a real number. So each xi is a real number. So what we have to show is that each of the elements after adding these two together is a real number. And then that's how we will show it's an element of Rn. So our first step is we need to use the definitions we were given. We were said x is an element of Rn and y is an element of Rn. So we can use the definition here to say, okay, if that is the case, then x has elements x1 to xn, and y has elements y1 to yn, where xi is in Rn and yi is an element of Rn for all I. Okay, so now that we've touched on the stuff we've been given, we can start to use the definition of vector addition for this. So, when it came to vector addition, we said that x plus y by definition, is going to be the sum of each of these elements. So it's going to be x1 plus y1 all the way down to xn plus yn. Okay, here's where we get to cheat a little bit, is that when you are doing these proofs, you are allowed to use all of the things you know about addition, multiplication, subtraction, division of just real numbers. So for instance, if xi is a real number and yi is a real number, then this means that xi plus yi is a real number. This is something you would learn in high school, right? If I take 1 and 2, they're both real numbers. So when I add them together, that's also a real number. You are allowed to use these in the scope of your linear algebra course, as long as it's stuff you learned in high school, right? Anything to do with real numbers, addition, subtraction, multiplication, you can do these without explaining. So, having known that, we can now state, therefore, xi plus yi is an element of Rn. Okay, but from our definition, this particular vector here has n elements of this form, where each of the summations of them are real numbers. Therefore, If each of the elements is a real number, then the addition of both of them together must be an Rn. The second one we're going to prove is known as the order of operations. So x plus y being added first and then z is the same as y and z be added first and then x afterwards. So this is the second kind of tool you can use when proving. In this particular one, we're not trying to show through a definition, we're trying to show a left-hand side and a right-hand side are the same. So how do we do this? We can simply just break it up. So let's do the left-hand side first. So from before, in the first part, we can basically say that x has x1 to xn, where each of these are real numbers. Y is equal to y1, yn, and z is equal to z1, zn. And then we'll say xi, yi, and zi are all real numbers for all I. Very small written, but the idea is we're writing down how each of them are breaking them into x1, xn, y1, yn, z1, zn, and each of those are real numbers using our definition that we were given at the beginning of the problem. Now that we've done that, we can do the left-hand side. So x plus y plus z is equal to, using vector addition, the definition we were given, adding x and y together is x1 plus y1 all the way down to xn plus yn, plus our vector z over here, which is going to be z1 to zn. Okay, now we can use the definition of vector addition again in order to do x1 plus y1 plus z1 and xn plus yn plus zn. Okay, so we've shown the left-hand side is each of the elements just added together. Now we need to do the same for the right-hand side. So the right-hand side we will use the blue color for. So right-hand side we have x plus y plus z is equal to our first one, which is x, plus, using vector addition, we can add these two together, y1 plus z1 all the way down to yn plus zn. Using vector addition again, we will have x1 plus y1 plus z1, xn plus yn plus zn. And now, since we have shown that both the left-hand side and the right-hand side are the same, we have proven the statement above that that x plus y first plus z is equal to y plus z and then plus x. Part 3 of our statement 3 is going to be us proving that x plus y is the same as y plus x. Again, using our definition before, we said we can break apart x and y. So using the definition of vector addition, we can say that x plus y is equal to x1 plus y1 all the way down to xn plus yn. Okay, here's where we're allowed to use what we know about real numbers. We know if we take two real numbers, in the question we were given c and d, we know that it's the same as the reverse of them. Now this is something we have known within the space of real numbers, so we're okay to use that here without any further explanation. This is stuff we can take as given and just use freely. So if I can flip the order of adding two real numbers together, again, these are just real, not Rn, I can do the same here. So I can flip the order of y1 and x1 and the order of yn and xn. Okay, so now using the reverse of the definition of vector addition, technically if I've got all the elements here in front and all the elements of x afterwards, this is the same as y and x. And that's our proof. So statement number 4 is our first example where we have a there exists for it, which means we need to find a zero vector, prove that it is an element of Rn, and then show that x plus that number, that vector, is going to be itself again. It's going to be x again. So for our proof, we're going to say let zero vector be something with n elements of 0. Now, in order to show that this is within Rn, we have to state that since the zero vector has n elements and 0 is a real number. Again, this 0 is the same for all of them. Therefore, the zero vector is an element of Rn. So let's go over that quickly. The definition of Rn stated that in order for a vector, in this case 0, which we've defined here to be n elements of 0, they have to be of the form xn to xn. Great, they've got n elements, that's the first one, where each of these are real numbers. So we stated this had n elements, and each of those elements is a real number. Therefore, our zero vector is a vector within Rn. Great, step 1's done. Now let's move on to the second. Now we need to show that x plus 0 is x. So let's take the left-hand side. We'll take x plus our 0 vector, and we'll use our definition of vector addition for it. So adding up each of the elements, we get x1 plus 0, xn plus 0. And using what we know about addition in real numbers is if we add by the 0 vector, it ends up just being itself. x1, xn. And that, where we defined it, is x. Okay, our fifth statement we need to prove is that for every single x within Rn, there exists an A that is also in Rn, such that adding the two together will become the zero vector we just defined in statement 4. So, the proofs when it comes to for all is we have to leave it as is. It has to be general, right? There's no restrictions we can play on it. This just has to be an element of Rn. Okay, now we need to find an A within Rn that we think will cancel out x. So let's say let A have n elements, which is negative x1 to negative xn. So the first part of ours is we need to prove that this is within xn. So the first thing we need to prove is that our A is an element of Rn. So we know that A, we'll say since A has n elements and negative xi, again, a real number times a real number we know is a real number. So negative xi is still a real number. So it has n elements. Each of those elements are real numbers. We'll say for all I equal to 1 up to n. Therefore, A is a vector in Rn. Now we need to prove the second part. So let's take our x and our A and add them together and see what we get. So using vector addition, we're going to take x1 plus our value here, negative x1, and xn plus negative xn. Again, we are freely allowed to use when we're adding or subtracting two real numbers together. We're allowed to just do this freely without any further explanation. So x1 plus minus x1 is technically x1 minus x1, so we get 0. Similarly for xn and xn and all the others. And since each of these are 0, as we defined in statement 4, that is our 0 vector. Our sixth statement is proving that a scalar times the vector x is within Rn. So, using our definition of scalar multiplication, we get c times x is equal to each of those elements within x multiplied by c, so cx1 all the way down to cxn. Again, using our definitions or our experience that we know within real numbers, c is a real number, x1 is a real number. Anything, a real number times a real number is still a real number. So we can state, without really having to say anything else for our proof, since cxi is a real number, comma, for all I equal to 1 and n, and cx has n elements, by the definition of xn, cx is an element of Rn. Statement number 7 is we're going to show that d times x and then times c is the same as c times d and then times x. So this one, we're going to do what we did in part 2, statement 2, is showing left-hand side and right-hand side. So our left-hand side, c, d times x and then times c, we'll do the inside first. So we've got, using our definition of scalar multiplication, we're going to take d and multiply it by each element within x. And then, using again the definition of scalar multiplication, we can take c and multiply it by each of the elements within dx. Great. Okay, now we can do the next side. Okay. So now taking c and d and then multiplying it by x. Technically, c and d are both a real number, so we can just, in one step, multiply both of these numbers into x. So we have cd x1 and cd xn. And since we have now shown that both of these are the same, we have proven statement 7. Okay, statement 8 is saying that c plus d times x is the same as c times x, and then using vector addition plus d times x. So let's do our left-hand side and our right-hand side again. So our c plus d is technically just a real number in itself, so we can go straight ahead and use scalar multiplication to do c plus d times x1, and then all the way down to c plus d times xn. Okay, now we can do the right-hand side. Leave it, please. Please, for right now. I'm almost done. Thank you. Berlin, 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 Berlin. Leave it, please. At least for now. Just for now. Just for a moment, please. Thank you. Sorry, Bob. And now we can do the right-hand side. So we take c times x plus d times x. We can do our scalar multiplication for each of these. So I will take c, multiply by each element of x for the first one, and then do the same for d for our second term. Then, using our definition of vector addition, we get cx1 plus dx1 all the way down to cxn plus dxn. And now just grouping these together, we'll get c plus d times x1 all the way down to c plus d times xn. And since we've shown both of these are the same, we have proven statement 8. Now we move on to statement 9. So, there's the idea of c times two vectors added together is the same as c times the first vector, and then using vector addition, c times the second one. Okay, so let's prove this again using our left hand and right hand side. So, the left hand side is going to be c times x plus y. We can use vector addition inside to get x1 plus y1, xn plus yn. And then we can use scalar multiplication to say that this is the same as c x1 plus y1 all the way down to c xn plus yn. And then breaking these apart, which will make the second part easier, is c x1 plus c y1 all the way down to c xn plus c yn. Now let's do the right-hand side. So, for the right-hand side, we have c times x plus c times y. We do our scalar multiplication for each, so cx1 all the way down to cxn, plus, we do the same to the second, our cy1 all the way down to cyn. And then we can use vector addition to add both of these together, and we'll get cx1 plus cy1, cxn plus cyn. And since we have shown both of these are the same, this statement is true. Our 10th and final statement of this extremely long theorem is going to be 1 times x is equal to the x itself. So this one's relatively straightforward. 1 is technically a real number, so we can use scalar multiplication for this. So 1 times x is equal to, now using scalar multiplication, we will have 1x1 all the way down to 1xn. And then, since now we're multiplying real number by real number, we can use what we learned in high school and all those rules with real numbers to say that this, we can just remove the 1 because it's redundant. So now 1 times a real number is just going to be that real number again. So 1 times x1 is x1, 1 times xn is xn, and everything in between is the same. So, since we defined x1 to xn before as the vector x, we now have back x. And we have proven our 10th and final statement. So let's summarize what we learned today. Basically, we went over an introduction into proofs, how we have to use definitions of other things that are stated throughout the problem in order to match the definition of whatever we are trying to prove. And using those both in tandem is how we end up making that connection and doing that full proof in math. We then got to talk about and use those proof ideas into an actual example. And in that example, we had 10 different statements we had to try and prove. We were able to use the definition form of proofs in order to show for Rn. We were able to show left-hand and right-hand side. And we were able to use all of our prior knowledge of adding, multiplying real numbers in order to prove all of those statements without adding any extra detail to it. These are the type of things you'll have to keep with you going on further into the course, and the stuff we'll be showing here in the next part. So, like, comment, and subscribe if you want to see more, and I hope to see you in Linear Algebra 101, Part 3. Bye for now.